This is Dr. Christy Patton-Lukes, and in this lesson we're going to be talking about where one can find C sub P and C sub V data, particularly with emphasis for the course for chemical engineering, material and energy balances. So in our last lesson we talked about how we can calculate changes in enthalpy and internal energy using specific heat data. And in particular, we find that delta U is equal to the integral from T1 to T2 of C sub V dt, where C sub V is the specific heat at constant volume. And this will be a true statement for ideal gases. It's pretty close for solids and liquids. And it's not too bad for real gases as long as you don't let the volume change too much. Now for changes in temperature, we find that delta H is the integral from T1 to T2 of C sub P dt, where C sub P is the specific heat for constant pressure. And again, this is going to be exactly true for ideal gases. It'll be all right for real gases as long as that pressure isn't changing very much. And for solids and liquids, we have an adaptation, which if pressure is constant will be delta H is Cp dt, the integral of that. But otherwise we would add on a term specific volume times delta P. The question though remains, where do we find the data for C sub P and C sub V? We're going to be looking at data specifically for this course in this textbook. But most of this is also generalizable, and I really actually recommend people hang on to this textbook for use in future courses because there are such great resources for data here. Now in the appendix, in particular for table B.2 is an awesome source where we have C sub P as a function of temperature for many substances. Now this table is like many other technical publications where the units, first of all, are going to be, stated in the heading, okay? So you've got to look up here and you need to see if you're Form 1 or Form 2. And so that's going to be in the first column here. And then there's constants A, B, C, D. If there's not anything shown there, then that means that those are 0. But the other really confusing thing is that you have to look at these headings. So right here for this first entry for B, what that says is B times 10 to the 5th equals 18.6. You want to know what B is, so solve like algebra. And we find that B is 18.6 times 10 to the minus 5. So be very careful when you read headings like this. If it's stated like this, then they're going to mean that you need to solve the little algebra problem. Other things to note on this table are that the temperature units are given. Sometimes they're in units of degrees C, sometimes in units of Kelvin. You need to use the appropriate units for temperature during that integration. So there's not like a single rule that you always have to use this. You have to use the appropriate units for the equation that you have. And the final things that I want to point out are that they're going to define for you the state and a range of where the temperature is valid or where the C sub P equation is valid. And so sometimes it's for liquid, sometimes it's for gas, and substances that can have two different states, they'll have one for each. For others, such as for air, we have it only as a gas, but there's still two equations. One's in degrees C, one's in degrees Kelvin, but they also have for slightly different temperature ranges, okay? They overlap, but really it's based on which temperature units you want. And some of them are for very tiny temperature ranges. So acetone, for instance, is only from -30 to 60 degrees C. But we have a different formula for gases from 0 to 1200 degrees C. And the reason for this difference would be simply that acetone won't exist as a liquid at those higher temperatures. Now, when using information from Table B2 or similar sources, the best results will come if you integrate first, right? We're doing this in delta H equals the integral from T1 to T2 of C sub P dt. So do the integration first and then plug in your limits of integration and subtract. This is going to get much better results than the alternative of saying, oh, well, C sub P is constant, so therefore delta H is C sub P delta T. This is only if you are very desperate, okay? It's never going to be as good unless you're talking about very tiny temperature changes. Now, if you're very desperate and you're going to this measure, that's one thing, but sometimes we're really even more desperate than that, and we have no data at all. Maybe it's a new compound that hasn't really been fully studied yet, and we're trying to get some approximate answers. Maybe you're just trying to do a quick estimate for something. And so there is something called Kopp's rule that can provide a very, very rough estimate. So Kopp's rule, table B10 is what you need to be able to do Kopp's rule. On this, what you're going to do is you look at a chemical compound and, like CO2, and you say, okay, well, it's got one carbon and it's got two oxygens. And so you would say, I guess I would do for solid CO2, the C sub P for each of the constituent atoms within the molecule, multiply by the appropriate number of molecule or atoms in the molecule. The units on this are going to be joules, and then it says per gram atom degrees C. In that case, what you want is this here, by the time you multiply by the number of atoms in the molecule, this is going to become equivalent to a gram mole. Okay, so it's a gram mole. So gram atom is a strange thing. It's that it's not a mole of the molecule, it's an atom within the molecule. So be very cautious with that. And one way that you can always test this is just try it on a substance. So if you'll look, I did it for solid H2O, also known as ice, okay? So 2 H's, 1 oxygen, gives me a value of 36.2 joules per something degrees C. So go and look up ice in a data table. And what you're going to see is that for mass units, it's 2.09 joules per gram degree C. For mole units, it's 37.6 joules per mole degree C. Ah, yes, this one is much closer to the prediction. And that's one way to kind of convince yourself that, no, really, this is a very cryptic way of saying a gram mole. So for ideal gases. Ideal gases are, again, not real, but they are predictable and they are useful estimates. One thing that is frequently done for many, many ideal gases is to use some very simple-minded estimates. So these are going to be based on the chemical structure, the molecule structure. So some molecules are monatomic. Okay, so helium is probably the best known example of that, but any of the noble gases would be a monatomic molecule. So in those cases, C sub P is going to be very close to 2.5 R, and you just choose the appropriate R for the units that you wish to have for C sub P. For polyatomic molecules that turn out to be linear, so like H2, anything with only 2 molecules will be in this situation. But something like CO2 where they all line up, okay? C sub P is going to be very close to 3.5 R. If they're polyatomic and nonlinear in an ideal gas, so CH4, right, they form a little cluster, or H2O where they form a little bent angle, then in those cases C sub P will be closer to 4R. Now these are going to only be approximate answers, but it's a good rough guess. Now this only gets me C sub V, so to find out what C sub P, to find out what C sub V is, we're going to take C sub p and subtract r to get C sub v. And again, this comes from the idea that delta H is delta U plus delta PV, and for an ideal gas, delta H is delta U plus R delta T. If I approximate this as delta T times C sub P, approximate this one as C sub V times delta T, we can see that we can subtract or divide through by delta T and then subtract to get C sub V is close to being equal to C sub P minus R. Now in general, finding C sub V is going to be much more challenging. Most systems are going to operate at steady state, okay? However, since there's a larger emphasis on small batch processes, particularly within, say, the biochemical engineering fields and some other areas, C sub V becomes much more important. So for solids and liquids, we're going to approximate this by taking C sub V and C sub P as being really virtually the same. For ideal gases, we're going to say C sub V is C sub P minus R. For real gases, we may take a complex form for what C sub P is equal to and subtract R as a first estimate, but this is always safer to find real data and find C sub V as a function of temperature. So finally, what about if you have a mixture? We're going to use a weighted average. And so you're just going to take molar mass fractions times C sub P of each of the components and add those up to get C sub P of the mixture. There's not a right or wrong way to do this, but if the units on C sub P are something such as joules per mole Kelvin, then this would be mole fractions. If the units on this are something like, we'll go with kilojoules per kilogram degree Kelvin, then this would be mass fractions. So use the appropriate type of fraction to match the units for C sub P. Now, this is going to be pretty good for things that are just a real mixture. When you have gases or solids dissolved into a liquid, just use C sub P data for the liquid form, even though it was maybe a gas or a solid that was dissolved in. You may just want to do C sub P and do enthalpy calculations for the primary component if it's just a small amount. This is a bigger topic for a future course. So I'm going to pause the video here. We're going to come back and look at a couple of examples in the next lessons.